Let's talk some more about the fundamental theorem of calculus. And right now we're going to talk about what's called the first fundamental theorem of calculus. I've written it out here to save a little bit of time, but it's the integral from a to b. But look at this carefully. This says we're taking the integral of f prime of x dx, and that is f of b minus f of a. And there's another convenient way that people write this. This big vertical line is called evaluation, and we evaluated b and we evaluated a and we take the difference. And so that's one of those kind of do the parentheses first things. And so there it is. So this sets up for us a little bit of an issue, which is in the problem here, we're given f prime and we need to find f. So instead of taking the derivative, we need to untake the derivative. And so some people have given this the rather awkward name of being an antiderivative. And there are a few that are well known. Any derivative formula becomes an antiderivative formula with one caveat. So let me write them down. I'm going to write them down the way they're typically written. Antiderivative of x to the n dx. So what you do is you write an integral, and but no indication of the domain, no a or b or no endpoints of the interval or no interval or anything. It's just, some people call it an indefinite integral. Anyway, x to the n, n is any power except minus 1. That's how I got this scar in 8th grade, which the formula for this is, it's a fraction. The top is x to the n plus 1. The bottom is n plus 1. And then there's a little bit of a surprise, which is plus a constant. That's an unknown constant. So we add 1 to the exponent, divide by the new exponent. That's the opposite of what happens when you take derivatives. And the problem is when you take derivatives, the derivative of a constant is 0. And so we have to leave room for this unknown constant, which in many problems we've got a lot of data to work out. This happened actually with differential equations. We didn't write it this way, but we had those initial conditions, and that determined the constant. So let me just highlight this as an unknown constant, and that leads to some funky things like twice an unknown constant, it's still an unknown constant. So if you have a factor of 2 in there, you just ignore it. So that's only because that's not a number, it's an unknown constant. So there's the deal. So that's the one of the most important antiderivative or integral formulas of x to a power. Of course, this doesn't work when n is minus 1. And so I'm going to just tell you what goes on when n is minus 1. X to the minus 1 is the same as 1 over x, and so I'm going to write it that way. And there's a little bit of a surprise here as well, is that you know the derivative of natural log is 1 over x, so antiderivative of 1 over x is natural log. But for reasons I'll get into in a minute, we need to take the absolute value of x, and so there it is. And of course, there's the plus c, because if you take the derivative of natural log of x plus 4, it's still 1 over x. Okay. Antiderivative or integral e to the x dx is e to the x plus c. Derivative of e to the x is e to the x. Antiderivative of e to the x is e to the x. I mean, we're just kind of stuck with that. And the last one, antiderivative of cosine of x dx is sine of x plus c. The derivative of sine is cosine, and so the antiderivative of cosine is sine. So there's the situation. If you're only taking one semester of calculus, there's not much more that needs to be done with these, because these are used for doing things in theory. And in ordinary engineering calculus, the last part of the first semester and the first part of the second semester, are devoted to what are called techniques of integration, where you learn all kinds of fascinating algebra tricks and fascinating algebra tricks. I happen to like them, but they're not very popular in the rest of the world. So but that's not, like if you're doing something with lab data, you're not going to be doing any kind of fancy technique of integration. So what you're going to end up doing is the following. What you want to do is you want to get integrals. This tells you, well, you could get the integral, because if you had the function f, you could plug in the endpoints and do the arithmetic, and you'd get the exact integral. But in a lot of cases, you have a passive function, so then you'd have to use something like trapezoid rule or Simpson's rule. And in a lot of cases, you don't need to know the exact thing. You only need to know what it is approximately. And so there's the situation. So here are the basics of doing antiderivatives. They're great for theory. They're useful in a few situations, but most of the time people in the laboratory or the real world are doing numerical integration. And that means doing it by computer. So this is a complete change right now. We're going to talk about integrals. This is antiderivatives, but we need to talk about integrals because what you're going to end up doing in whatever it is that you're studying is integrals. And that means getting a number. And so I want to spend some time talking about how to do that. The typical way that happens in calculus courses of getting a number is you take out your graphing calculator and you do the stuff, whatever different brands of calculators have different kind of languages for doing this, and you do the stuff, and then you get something that you need to copy out because it's the calculators on purpose. These are made for profit. You're not supposed to be able to get things out of the calculator so that you can't cheat on exams or something. I don't know. We're not teaching you about exams. We're teaching you about using calculus in real life. So, and besides, so I was going to show you how to do one with a graphing calculator, but I'm at home and I can't find a working graphing calculator in my home. So what is it that I do? Well, first of all, I know a bazillion bags of tricks because I've been teaching math for a century. And so there are a lot of times that I can do integrals using paper and pencil, or at least good approximations. Not trapezoid rule. Trapezoid rule, you know, if you wanted to do 100 subdivisions, that's just way too much work. So what I want to show you is something that is not a graphing calculator. It's not a commercial product. This is a website. You can get at it from anywhere in the world, even on the International Space Station. And so there it is. It's called Sage Math. And if you look up at the top, you can see the URL. This is Sage, sorry. Sage Math. Okay. That's what happens with touch screens. You can see at the top, sagecell.sagemath.org. I'm trying to make it so you can see it. And you get this little box. And what I've done is I've typed in a function. And the function I've typed in is very important if you've taken any statistics, or even if you haven't taken statistics. This is the standard normal distribution. It's the most important function in statistics, period. So I've typed it in. And you have to type it in like you're doing math, and you have to be aware that you have to say it's a product, or you're not talking to a person who knows that you mean it's a product. And sometimes the keys are a little hard to find, but they're not that bad. So anyway, let's just read this function out loud. There's a coefficient, it's a fraction. Top is 1, the bottom is the square root of 2 pi. Where did that come from? Well, when we study distributions, I'll explain that. And then we're integrating e to a power, and the power is a negative fraction. Top of the fraction is x squared and the bottom is 2. And so that's the standard normal distribution, a very, very, very important function. And the reason I want to highlight this, besides its importance in so many applications, is that you can't do the antiderivative using the fundamental theorem of calculus. That's something that math majors should learn how to prove. And it doesn't matter whether we can prove it or not. You won't be able to do it. We're not going to study the techniques, and nobody can do it. It's not possible to do this antiderivative except by numerical methods. So let me just write down what the function is. First of all, it's sagecell.sagemath.org. What Sage is a bunch of people. It's open source software like Linux, and it's a bunch of people who've gotten together over the years and have developed really good open access mathematical software, calculational software. So this is how we can get things done. Okay. And then let me write down this integral in normal, not computer terms. So this is the standard normal distribution. I've got it written there. And now I'd like to just calculate. Well, I can't do it. I would like to ask Sage to calculate a few of these. If you've taken statistics, you're going to recognize what comes out of this. So the Sage function for doing numerical integrals is called numerical integral. And so let me get that in here. So, and it's a pretty straightforward thing if you can get away from the glare. It says numerical underscore integral. And you've got the function and the limits of integration, or the endpoints of the cell that, of the interval that you're integrating over. And so I'm taking f from, I can't read it in that, from -1 to 1. Okay, perfect. And then with Sage Cell, if you've done this right, you hit evaluate. There. Oh, sorry. I'm sorry. There was an extra thing in there. So let me hit evaluate again. And it comes out with two numbers. Those aren't an ordered pair. There they are at the bottom. They aren't an ordered pair. They're the integral and the error from the method of integration. This uses a much fancier method of integration than we're going to have time to study. So this is saying the integral is 0.68. If you've taken statistics, 68% is a very important number. You know that. And the error is e to the minus 15th, 15 places of accuracy. Woo! Okay, so let me edit this a little bit and do a little bit more. That's one of the fun things that you can do with these calculational tools, is I'm going to take the integral from -2 to 2. And so I just put in -2 to 2 and hit evaluate. And almost before I can get it up on the screen, it comes up to, looks like 0.95. If you've taken statistics, 95%, 2 standard deviations. And the error is a little bit bigger. It's only 14 places of accuracy. Where's the world going? And let me do one more, because these are such important integrals for all kinds of applications. Being able to work with this integral is one of the keys to doing statistics. So I'm going to do from -3 to 3. I'm going to hit evaluate out of sight. And here it comes, 99.7. So 68%, 0.68 from -1 to 1. 95% from -2 to 2, and 99.7% from -3 to 3. If you've taken statistics, you're going to go, oh, I know now where those numbers came from. So this is the way that people do integrals in real life. I mean, if you're forecasting the weather, you've got to do a bazillion of them. You have to do something more complicated. But this is a good way to do it. It's free. It's accessible from everywhere, including the International Space Station, and it gives super accurate results. We don't have to worry about the algebra of doing antiderivatives. If you get into that, then you're just going to have to study more. But that's really not part of a 1 semester course. So, okay, let's all go and be sages.